Hi, in this video, I'll explain the rational root theorem, also called the rational root test. Let's first set up what it's about. It's about polynomial equations where all the coefficients are integers, something like these two. They are polynomials and all their coefficients are integers. What the rational root theorem does is that it helps us look for any roots, meaning any solutions that are rational numbers, if any exists. It goes like this. Given a polynomial equation with integer coefficients like that, with an, x to the n, all the way down to a1x plus a0 equals 0, where all the ai's are integers. If the equation has a rational root p over q that's fully reduced, then first, the numerator p will be a factor of the constant term a0, and the denominator q is a factor of the leading term a sub n. Since a factor could be either positive or negative, I like to think of it this way, that the rational root is plus or minus factor of a constant divided by a factor of the leading. Let's box this up and apply it to the two examples we saw earlier. Example 1, x squared plus 2x minus 15 equals 0. What the theorem says is that if this equation has a rational root, it will have to be the form of factor of constant over factor of leading. The constant term, a0, is equal to negative 15. But in my head, I don't need to worry about that negative because I already got it taken care of over here with the plus or minus. The factors of 15 are always start with the number itself and always end with 1. So don't forget the number itself and 1. And then think about everything else. Well, there's a 5 and there's a 3, and that's pretty much it. The leading term, a sub n, is equal to 1. There's a 1 right here. So there's only one factor, 1. So the possible rational roots are plus or minus 15 over 1, which is plus or minus 15, plus or minus 5 over 1. So that's just plus or minus 5, plus or minus 3, and plus or minus 1. So there are 8 possibilities. 1, 2, 3, 4, 5, 6, 7, 8. The 8 possibilities, we can plug them all in to find out which one is a root. First, x equals 15. 15 squared is 225. I could compute this, but I don't really have to. I see 2 very large positive number and it subtracts 15. So I just know that it's going to be something positive. Specifically, it's positive 240, but I really don't need the number 240. I just need to know that it's not 0. Something positive and not 0. So x equals 15 is not a root. X equals negative 15, also positive, not a root. Five squared is 25. It's also positive, not a root. Now try x equals negative 5. Ooh, this is 0. So x equals negative 5 is a root. Next, I have plus or minus 3 and plus or minus 1. Three squared is 9. 9 plus 6 minus 15 is 0. So x equals 3 is also a root. At this point, since the equation is quadratic of degree 2, and I already found 2 roots, I really don't need to go on, but for sake of completeness, just to show you how this works, I'm going to go through the rest of the possibilities. 9 minus 6 minus 15, some negative number, that's not a root. Okay, 1 squared is 1. So yeah, nothing else, as expected. X equals -5 and x equals 3 are the roots. So that's sort of the idea of the rational root theorem. I look at the equation, I make sure it's polynomial with integer coefficients. I list out all the possible rational roots and I check them. If I find any, then that's the rational root. If I don't find any, then I know that the equation does not have any rational roots, meaning that its roots may be irrational or may be complex. But whatever it is, it's not going to be rational. Let's now move on to the second example that we saw earlier. This is a typical homework quiz or exam question involving the rational root theorem. First, they ask you to determine all the possible rational roots of the equation, meaning you just list out all the plus or minus, and then numerator over denominator, all the plus and minus possibilities. And sometimes, not always, but sometimes they'll ask you to do a second part, that is to find all the rational roots by plugging in all of those possibilities and see which ones work out. Now, the root of an equation is also the zero of a function. So sometimes the question comes up like this. It's the same question, but instead of asking about the roots of an equation, they'll just ask about the zeros of a function. Either way, the approach is exactly the same. The rational root, or zero, is plus or minus factor of constant divided by factor of leading. Here, the constant is equal to 1, so the factor is 1. Leading is 2. So there are two factors, 2 and 1. So the possibilities are plus or minus 1 over 2 and plus or minus 1 over 1, which is just plus or minus 1. So there are 4 numbers to check. X equals 1/2, x equals -1/2, x equals 1, and x equals -1. And just as a reminder, the function is 2x cubed minus 7x squared plus x plus 1. So this is 2 times 1/8 minus 7 times 1/4 plus 1/2 plus 1. 2 times 1/8 is 1/4 minus 7/4 plus 1/2 plus 1. And this is -6/4 plus 1/2. 1/2 is actually 2/4 plus 1. 1 is actually 4/4. So it actually is equal to 0. So that's kind of cool. We right off the bat, and we found a rational root. Right, for x equals -1/2, and I see a bunch of negative. I don't need to calculate this out. I know that it's some negative number, and also it's also some sort of fraction. It's not going to be 0. For x equals 1, have 2 times 1 minus 7 plus 1 plus 1, -3. So no. X equals -1. And it too is something negative, so no. and therefore x equals 1/2 is the only rational root. If I want to find all roots, I can take the original equation and I divide it by x minus this number. Using either long division or synthetic division. The original polynomial is degree 3. I divide it by x minus 1/2. I'll end up with something of degree 2. And then I can solve using the quadratic equation. If you want to go ahead and do that, then hit pause because spoiler alert, if you work on that, you will find that the remaining roots are 3 plus or minus square root of 13 divided by 2. In other words, the other two roots are irrational. The rational root theorem works out that there is one rational root and we found it and it's the only one. Now, how do I remember that it's plus or minus factor of constant divided by factor of leading and not the other way around? I'm able to remember that because in my mind, I think of the simplest polynomial equation, mx plus b equals 0. Then the solution to this is negative b over m. B is the constant and m is the leading. So it's constant over leading and not the other way around. My own little memory trick. All right, last example. Determine all possible rational roots of this equation, x cubed plus x squared over 6 minus 7/6x plus 1/3 equals 0. The problem with this equation is that it does not fit the requirements of the rational root theorem. The rational root theorem requires a polynomial equation, and this is polynomial, so that's good. But the coefficients must be all integers, and several of these coefficients are not integers. Well, there's a way around that. If we multiply both sides by the least common denominator, then all denominators are gone. The LCD here is 6, so I'm going to multiply both sides by 6. I end up with 6x cubed plus x squared minus 7x plus 2 equals 0. So now it's all integers. I can apply the rational root theorem, plus or minus factor of constant over factor of leading. Constant equals 2, so the factors are 2 and 1. Leading is 6, so the factors are 6, 3, 2, 1. Possible rational roots. I'm first gonna take the numerator of 2, and then I go through all the possible denominators. And then I go through the numerator of 1 and all the possible denominators. And now I take this list and I sort of simplify them. Plus or minus 1/3, plus or minus 2/3, plus or minus 1, plus or minus 2, plus or minus 1/6, plus or minus 1/3, but I already have, so I'm not writing it down again. Plus or minus 1/2, and plus or minus 1 that I already have. 12 possibilities. If you want to, you can go ahead and try plugging in and see which of these numbers works out as a rational root. Spoiler alert again, the rational root is positive 1/3, and the other two roots are irrational. All right, hope that helps. In my next video, I'll apply the rational root theorem to a theoretical results so that you see that this theorem is more than just listing out a bunch of fractions and doing a bunch of tedious calculations. It has theoretical applications as well. All right, subscribe for more contents. Thanks for watching. Bye.